right? And we've seen so far, well, only with the quadratic utility and linear mass, right? Of Kuhn-Hamilton with differential products like sin and Vives. Remember? Okay. We remember that, and that was called the representative consumer approach. Right? We have a utility function that represents the heterogeneity of the consumers and how they use the different products, and basically gives us demands that implicitly have product differentiation. The other approach is discrete choice, where each consumer chooses among several products. Right? And the heterogeneity of the consumers are heterogeneous. Because, for example, the only model we've seen so far, totally, they are like distributed uniformly on a line, right? And that's consumer heterogeneity, right? Because that means some consumers are here, some consumers are here. They're at a different distance from the firms. We can interpret this metaphorically or literally, right? Like the Saudi Arabia line project. So far, the line hasn't been built, so it is metaphorical. Okay? And then we tried to solve the model, and we got midway. The algebra started getting complicated, and I think they should finish. So the model that we did solve was the hoteling without price competition, right? Where the price was exogenous and the firms are the pure location, right? So we have hoteling, linear city, and then we have the pure location. This is like from the service. This is like from 1931. And we had pure location. Now the positive problem set, and we still have it in paper here, like makes sense on one side. And we also have positive solutions, but we don't need them. I don't know if you guys solve it. Do you guys have them? Yes. It's okay. You guys have the solutions to the problem set?
We have them.
Yeah, you have them? Okay. Because I
haven't seen them.
accidentally,
I think we have them.
I forgot to take them out and then I saw. But people have them. That's okay. At this point, it doesn't matter. It's like my bad, basically. I should have checked exactly. Basically, my course from last year just got copied to this year automatically. I didn't do anything. And then on ADI, and then like it had already the stuff that I wasn't supposed to show you yet, like the solutions to the concept. But don't worry about it. It's okay. It's like a problem set. Basically, this class is based mostly on a final exam. 70% of the grade, and all the grade heterogeneity mainly comes always from the final exam. The problem sets are just there to help you. So the problem sets give you like a free 30% of the grade, so you guys don't get stressed out. And it gives you an opportunity to practice. Okay, so basically don't look at the solutions, handling the problem set. Okay, I'm not gonna like be grading everything during the problem set, but I want you guys to have an opportunity to basically have a workflow here where like you don't just go and study straight for the final exam. Okay? So do the problem sets. We do it, then we look at it, we see if you have any doubts on Wednesday, and that's it. And then you guys try not to look at the solutions before Wednesday. Okay? Try to do it and then hand it.
And we send you by email, right?
Sorry?
We send you by email or?
No, give it to me on paper.
Okay, great.
Okay.
Great.
So try to do the problem set without looking at the solutions for Wednesday, and then Wednesday I'll post the solutions again, and for those who were like fast and downloaded them, then you will look at them anyway. But try not to look at them. Try to solve the problems. It's a way to practice for the exam, which is what really matters. Okay? Is this really getting that definitely these are the solutions? Okay, it's kind of like there's no mystery now. I feel bad. I mean, help me. It's okay.
Yeah, it's okay.
Okay. It's okay. The problem sets were never supposed to be like a competition to see who could like solve the most. I mean, it was always supposed to be a way to just work step by step and give you a chance to practice. Okay? So you can practice and you know that the solutions are there. Try not to look at them and try to practice and think about the problems and how you can solve them. Okay? And then basically it doesn't matter if you solve like half of the problem set or all of the problem set. Do what you can. Okay? It's just like a space that's there for you to practice. That's like, think of the problem set as like free 30% of the grade, because this class can get hard, and I don't want people to like be super stressed out. And then 70% still there for you guys to like prove that you're the best of the best.
I have a question. Now that you mentioned the exam, which are like the type of questions we're gonna find on the exam, or if there is any, I don't know, any model or question or whatever?
Basically, that's what the problem is for.
Okay.
They're gonna be like the problems. Okay. Now the problem set has some questions that have maybe a little bit more algebra that I would like to put in the exam. So maybe it will take longer to the problem set. Maybe the problem set takes you 4 hours to solve, and the exam is not going to take you 4 hours. Okay, it's going to take like 1 hour and a half, 2 hours, and I will give you like 2 hours and a half. Okay, the idea of the exam is not that these things can take time, as we saw this class in the hospital, right? So in the problem set you have more time, the exam you have less time, but the idea is this type of problems. Okay, the exam is going to be like old-fashioned oligopoly models with some kind of twist, and you have to solve it by hand, on the paper. There's 2 ways to deal with AI in education. One is to go full AI, and we're doing that with the undergrads for this programming class and machine learning. The other one is to go fully like medieval. And this one is more medieval. Okay? So this course is more like the Middle Ages. That's our approach. And it's always been that way, and we're like, you know what, actually this course is based on an exam basically. The problem sets were never core to like the grading. The core of the grading is an exam, closed book, in person, on paper, and it's always been that way. And that's AI proof. Actually. So it forces you to study the old-fashioned way. Unless you can ask ChatGPT if you have a doubt and if it can explain to you something of the hotel world and stuff. That's almost a clear book. Okay, so the pure location model, if you remember, any questions on the examination and the grading of the class?
No, just to tell you, we already have our room in an hour. It's M4 and 9 something. It's 9, I think.
Great.
The 23rd of March, as we agreed.
Great.
It's already in the calendar.
March 23rd. Room 4.
Yeah,
At what time?
I've copied.
Wait, on what time?
9, I think.
9 a.m.
Yeah.
9 to 12 says on the.
Maybe Carmen will
doesn't
give you the
need-
exams and I'll come at 9:30 because I have to drop off the kids at school.
Yeah.
Okay, so I don't know if I can be here at 9. But anyway, that's what, let's not change it, and maybe Carmen will have to come, or Javier, or someone will do the exams.
Or we can
start
just
this
move
time.
it 9:30.
Or
It's
we
9 to
we have 3 hours slot, so we can do it 9:30
That's
to
true,
12.
we'll do 9:30
To
from
12.
9:30 to 12, that's it.
Okay, yeah, we have it 9 to 12, so that's
Okay.
great.
Perfect. So basically, we have 2 firms, and they're choosing where to locate. In here, we said, okay, it seemed like anything that was symmetric, like 1/3, 2/3, could be an equilibrium, but then we showed that it's not, right? Because here, basically, we talked about the concept of Nash equilibrium, right? What's a Nash equilibrium? A Nash equilibrium is, mathematically speaking, a fixed point of the best response functions. Okay? A Nash equilibrium, let me repeat that. A Nash equilibrium is a fixed point of the best response functions. Okay? So if we have two identical firms, let's say, right? I give Bertrand, and here we have the price of the other firm, right? The price of J, and here the price of I. The best response function is something like this, right? This is the best response for I as a function of Bj. Then the Nash equilibrium is where this closes the 45-degree line. Why? Because that's the fixed point, right? Pj and we have pi, right? And pi here is going to be equal to, and this is equal to our two symmetric firms. Pi, this is where pi is equal to the Nash response of Pj. Let's call it now P star, right? P Nash. P star is equals the Nash response to P star. Okay? If the firms are symmetric, you can think of it this way. It's basically, if this is the price that the other firm sets, that's the price that I want to set. And then that means if I now say, okay, what does the other firm want to do? If I put this price, the other firm is symmetric. So if I set this price, the other firm also wants to set that price. So it's an equilibrium. You see, in a very real sense. It's like it stays there. Nobody wants to change. If we're at the fixed point already suggests equilibrium. Right? And then if the firms were asymmetric, I still stack the best responses, right? So we have like a vector of prices, P1, P2, up to Pn, right? If these are the prices of the firms, then I can say for firm 1, what's the best response to these other prices? If I expect these other prices for the other firms, right? So I can have like a best response of this, and then I can have like what price would firm 1 set if I have these prices for the other firms, right? Well, it would be the best response to these prices, right? And the price from 2 would set would be the best response to these and these prices. And then and so on up to Pn, right? And Pn would be the best response to the prices of all the firms except itself. And then it's kind of redundant, you can make the function also including your own price, right? But your own price here is just kind of like a lambda, right? We have the multivariate best response function that gives us, given the expectation for what's going to happen, what do firms do, right? And basically, we can kind of iterate. We can start with some guess of the prices, right? And do the best response function, and then say, okay, these will be the prices that will respond to those prices, and then we plug them back in, and then we start iterating, and hopefully they will converge to something, to some point where like if they play this price vector, right, P star, then if they expect this star to play as a vector of prices, then they will play P star, right? This is a fixed point, right? And that's the Nash equilibrium. It's a P star such that P star is equal to the best response to P star. When they expect this to happen, they want to play that, right? And they don't want to change. If somebody has an incentive to change, if they expect that, then that's not an equilibrium because that's not going to happen. You see what I mean? It's something where like, if we expect that to happen, we still play that. You see what I mean? Fixed point, right? And so these 1/3 and 2/3 is not a fixed point because if you expect to play 1/3 and 2/3, this one's going to move over here and this one's going to move over here until it's getting closer to the median. And when we get to 1/2, that's going to be a fixed point because if they both expect to be at the center, like one is slightly to the left and one is slightly to the right, then this one gets this one gets half here. Nobody has an incentive to change, right? So this one is a fixed point of the best response functions. And therefore it's a Nash equilibrium. Okay? Of the pure location mean. Now in 1951, Downs applied this pure location model where there's no prices. He said, okay, this has a nice application and it's simpler than the Hodgkin model with prices. That application, Downs was not an economist, but a political scientist. Okay? Political science. And basically the idea is that voters are distributed from left to right on a line. Okay? So some people are more to the left, some people more to the right, some people in the center. Right? And suppose we have two political parties that are choosing where they're going to locate their kind of like ideological reputation, right? Their commitment to their kind of reputation for where they are on the left or the right. And if there's just two political parties, they're gonna, in this simple model, they're both going to locate. One is gonna like slide to the left or the center, and the other is gonna locate slightly to the right of the center, right? So when you have like two parties that are almost identical, it's just that they're just gonna be different colors, right? One of them could be like red, and the other one could be like blue.
Like in the States.
Like in the States or in Spain too, right? And so we have like PSOE and we have blue PSOE. But in Spain it's much more complicated because we have a lot more parties. We don't want to go there. I mean, we want to go to Spain for vacation, to the beach, and stuff. We don't want to model all of Spain. And basically, this is just a very simple model that gives you like an insight. Here, that's the median voter theory. Okay, they go to the median, the one graph. So that's the median. It's kind of like an application of the hotel location model. It could be like people trying to sell ice cream on the beach, and where they're gonna like be trying to sell the ice cream, or it could be where the political parties locate. Okay, it's an application of the location model. Probably differentiation, but in the end they don't really differentiate. But obviously that's more complicated than that, not so simple. Okay. But the parties want to be where the people are. Okay, endogenously, the candidates, it's not like the candidates in politics, it's not like they're like, this is what I believe. Well, they could, it also could be that. It could be like, you could think of this in two ways actually. You could think of it as like, politicians have no scruples and they don't really have a real ideology. They're just strategic and they're like, I'm gonna say what I need to get the votes, right? And I know that I'm gonna get more votes if I'm kind of in the middle, because if I go too much to the left, right, then I'm leaving a lot of political space here, and this party can locate here, and get all the votes from these like center left voters, right? That would have voted for me, but now I went too far to the left, right? So there's a tendency that I don't want to go too far to the left, because then I lose the center left voters, right? And I'm leaving that space open for the other party, right? For the center right party.
But that only happens if we are assuming a uniform distribution. So what model can we use if the data is bimodal, which in this case it is?
This happens when?
Only
the uniform.
Yeah, only it's.
Well, the uniform, it doesn't have to be uniform. It's not, this result is more general than the uniform.
Because if you have two peaks, then it will not work.
Oh, yeah, this happens if the voter preferences have to be single peaked over the issue. So they have to distribute on the line over the preferences, and the preferences have to be single peaked. But it doesn't have to be uniform. It's true, there are some technical constraints on the distribution of the voters. So this doesn't, you don't always get the median voter result, that's true. But it's not required that they have to be unique. You could have them be like this. As you're saying, if they were like, if the voters were distributed like this, then that would be the problem for the median voter. You could get something else. You could have Libya, or you could have one party here, one party here. Right? But if they're single peaked, then they're going to want to go to the median of the distribution. In the uniform, the median is at 1/2, because it's symmetrical. Okay, so that's an application, just to say, sometimes models have applications that go a little beyond scanners, right? So that's what we thought of before. But then now we have to solve the model with prices, right? Because in the end we care about the economic measure, we care about the pricing, right? And the pricing makes it more interesting because it breaks this median tendency actually. Because then they don't just want to be, now the firms have a dilemma, right? It's like, I want to be in the middle, close to all the consumers, but I don't want to be close to my competitors because I know that in the second stage, the competition is going to be too tough, right? If I go, and suppose there's like in the center of the city, if if I go to like the, I don't know, the center of Madrid, right? And I open, I say, suppose I want to sell chocolate con churros. Okay, you guys know what is chocolate con churros? Classic Spanish Madrid thing, you know, tourist trap.
Tourist trap.
So,
I'm not gonna.
we're starting Monday like hard with everything.
Of course.
So, okay, so you have like the market for the chocolate con churros, right? And there's gonna be like the Ginés, San Ginés, and Mallorquina. I don't know. There's a couple of famous places, right? And they're all kind of close to each other because that's where all the tourists are, right? So if you want to attract the tourists, you have to be there. But there's already a lot of them. So if you want to open a chocolate con churros, maybe that's not the best place. You have this dilemma. Maybe yes, because that's where the tourists are, and there's space for one more. But maybe you want to open your chocolate con churros in a place. You look at the map and you look at chocolate con churros and where all they are. And you're like, well, I would like to be in a place that has a good amount of tourists, but maybe where there isn't really an excellent chocolate con churros place yet, right? That's what people do when they try to open their business. They don't say, okay, that's where they are. That's where they have to look at where they open spaces as well, right? It's a trade-off between customers and competitors, and obviously the places where like already have the customers is where most of the incumbent competitors are going to be. So you have to find, it's not so easy, you have to find the places that are a bit off equilibrium, or where you kind of be like, okay, where could I go, right? That's underexploited. And that's kind of like what you see mathematically in the model of hoteling with product location stage and then the pricing stage. And actually what you're going to see exactly with the pricing stage, they're going to differentiate as far as possible in the 0-1, but you could extend the model in a way that it's kind of like an intermediate. Okay. And then we started saying, okay, how do we do this? If we have linear transportation cost, as we saw, the model is badly behaved because there's like this discontinuity, right? At some point, if I reduce the price, there's a point where like there's a jump in my demand function, and I get all the customers at the same time. Remember this?
Yeah.
So let me take that up. How do we have it? But we started with the other and we could finish. So I mean, I guess we should take off from where we ended, or maybe we should do it all again. We'll try to be more efficient. But why don't we do it all just to fix concepts?
Yeah, because if not, we're gonna start lost. I think.
That was going to be lost. So whereas the hoteling basically, what we said is there's a utility, right, for ride, and that's going to be your reservation utility R, which is how much the good itself is worth, and then you have to pay for the good some price, and then you have the transportation cost, right, which is going to be now times the distance between the customer, X, and from R squared. Okay, so that's what this is the quadratic transportation cost. Okay, and then we said basically they're in line, right? 0, 1, and it's going to be this is the location from 1 and this is the location from 2. The total price that they pay is the price of from 1 plus the transportation cost times x minus the 1 squared. And that's going to make it quadratic here, right? This is like the total cost of buying from that firm. And then that's going to be like the price of from 2 plus tau times x minus 2. So for customer X, it's going to make it quadratic, and at some point we're going to cut right here. Okay, so we need to find the indifferent consumer X hat. And for that, we're gonna basically equate X hat is for the one where P1 plus tau times X hat minus L1 squared is equal to P2 plus tau times X hat minus L2 squared. Okay, basically where the price plus the transportation cost are the same. Okay, this consumer is indifferent between the two. And the ones that are below X hat, these buy from firm 1, and then the ones that are above buy from firm 2. This has mass X hat, and this has mass 1 minus X hat. Right? We want it as like the integral and so on, and here it's the trivial integral. And so now we have to solve this. And when we started doing that, we realized that we expanded the square, right? And then that means like the x, at least the x squared cancels out. So that simplified our life a little bit. So we have tau times minus 2 x hat L1 plus L1 squared. And here we got P2 as tau times minus 2 x hat L2 plus L2 squared. Okay, I already cancelled out the x hat squared terms that appear here and here with this expansion. So far so good. And now we have to solve for x hat. Okay, to obtain the demand from 1, and we have to do 1 minus x hat to obtain the demand from 2. So the only things that has x hat here is this minus 2 x hat L1, so I'm going to put it there, and I'm going to bring everything that doesn't have x hat this way, right? So actually no, I'm going to bring this one here, because L2, we're going to work with the, under the assumption that L2 is greater than L2 L1. Okay, just without loss of generality, just to name the firm, say, okay, there's the firm that's on the right, that's on the left. Okay, it's arbitrary. We're going to call the firm 2 the one that's on the right. That's not. Okay, so then, like in the drawing. So then I'm bringing this one here, and then we're going to have 2 times 2 tau times L2 minus L1 times x hat is equal to P2 minus P1 plus tau times L2 squared minus L1 squared. Okay, and now x hat is equal to P2 minus P1 over 2 tau L2 minus L1 plus the tau cancels out here, and L2 minus L1 is L2 squared minus L1 squared is L2 minus L1 times L2 plus L1. So that's going to cancel out, and then we're going to get L2 plus L1 divided by 2. Okay, so linear demands, if the prices are the same, the different consumers are in the middle, right, of the two firms, L2 plus L1 over 2. And then if your price goes up, you have less customers, there's some slope, right, 1 over 2 tau times L2 minus L1. And if the price of the other one goes up, you get more customers, right, because these things like growth. And if you increase the price, then you're going to cut like to the left, right? Okay, enough intuition, time for algebra. Okay, so that's x hat, and now we need to do 1 minus x hat. Just to be complete. So 1 minus x hat is going to be equal to 1 minus this, 1 minus L2 plus L1 over 2. Plus P1 minus P2 over 2 tau times L2 minus L1, and this is equal to basically P1 minus P2 over 2 tau L2 minus L1 plus, instead of L2 plus L1, it's going to be 1 minus L1 plus 1 minus L2 over 2. Okay, so it's the average of locations, but see, as if we flipped, but it's the same thing, basically. If the prices are the same, they're going to be located in the middle, in between them, because really the one cancels out. No, no, it doesn't. It doesn't cancel. But you can think of these as the locations that counting not from the 0 but from the 1. It's like the mirror image of the locations. So now we have the demands, exact and 1 minus exact for the two frames.
What if L2 and L1 were the same?
If L2 and L1 were the same,
We have a problem.
there's no problem. It's 1/2. Then no 1/2.
But in the other one, the denominator is 0.
Oh. Yeah.
There's a problem.
Well, there's a problem.
Just a
But-
minor discontinuity.
Okay, but fair. Where's the different consumer if the two firms are located in the same place and the demands are different and the prices are different? Okay.
In the lowest price.
Okay, fine. We'll consider your limit case where the two are the same. No problem.
We'll go to the lowest.
Maybe there's something to be learned from this. What happens if the two are in the same location? Exactly the same.
I go to the one that is cheaper.
Considering these are continuous like demand functions, really well behaved, right? But then it becomes not well behaved because it becomes like homogeneous goods per trend. You see what I mean? And then there's a discontinuity in the demands. If my price is higher, I get 0. If my price is the same, I get half. Right?
And if my price is lower, I get all.
And if the price is lower, then I get all of the demand. Actually, if the prices are the same, it's not really well defined. It's like a limit between 0 and 1, right? And we can assume that it's half, or it could be 1/3. It's actually arbitrary. Like it's exactly the same as in homogeneous goods per trend.
Okay.
I have to say, as a rule, you get half, but I could say you get 1/3. Okay? If the consumers are different, they're different, they flip a coin. It could be a fair coin, it could be an unfair coin. Okay? There is a limit, and the limit is not well defined because one of them is 1 and the other one is like 0. You see what I mean?
So basically anything can happen.
No, it's not like anything can happen. But well, yeah, if they are the same and the prices are the same, anything between 0 and 1. And if the prices are not the same, one is 1,
Of course,
the
and
other
one
is
is
0.
0.
Okay, it's like this. So then again, there is continuity in the demand functions. Okay,
So in that case.
and the reason, sorry, and the reason we get this thing is because I implicitly may have cancelled out L2 minus L1, because when I divided by L2 minus L1, that's not allowed, mathematically speaking, when L2 is equal to L1, because then it's divided by 0, right? So here I divided by 0 in that case. So in that case, I have to consider the first condition, I have to look at it and consider, okay, I cannot solve for exact the first condition. I have to think about what's going on and do a separate case.
I mean, yeah, you could simply remove.
No, it says like, I can't solve for exact because solving for exact requires divided by 0. 1 and 2 is equal to 1. So this is here, to get from this up to here is okay. Here, but here is if you're assuming L2 is different from this time.
Or maybe just like L2 is strictly higher than L1.
Or we could say that without loss of generality, L2 is strictly higher than 1. Just to kind of name the things. Okay?
So what he's saying is we return to the Bertrand model. That's when locations are equal to each other.
If L2
We return to
and
the
L1,
Bertrand model.
the products are homogeneous.
Right.
And they compete prices in the second stage. So if they have a homogeneous product, in this case, homogeneous, the only dimension of differentiation is location. The locations are the same. The pricing game is homogeneous per run. There's no dimension of differentiation in that case. But they're going to choose to differentiate. Maybe. We'll see. Okay, so yes, very important. Thank you for making that point. If L2 equal to L1, then with homogeneous goods Bertrand, the second stage, price is going to equal marginal cost. The second stage. In the pricing game. Okay. Marginal cost, in this case, we assume that it's 0. So the price will be 0 if they do that. Okay.
Because we
So
are
that's the thing.
assuming
I mean, this ties it all together. This was amazing. Because here, in the pure location game, we had some exogenous with the price minus the C, and we had like the taxes, right? We just said that this is what how much we're gonna make, and then I just have to decide where we're gonna locate, and then they locate in the middle, right? Because they don't care now, because they have like this little cartel in this on stage, and they just set the price exogenous, right? So then we don't care, we locate in the middle where the people are, and we still get it. We still don't go to how much resource per turn because there's no second stage game. Here, if they locate in the middle, they get 0. So now I have to think, well, if I do that, in the second stage I'm going to get 0. So do I really want to do that? Do I really want to do right next? Is that going to be a magic rule? If I expect the others to be in the middle, I'm going to be in the middle, and then we're both going to get 0? Or could I do better? I don't know. Because there's some results where like they make 0 in return, right? So it's like, but now clearly they have an incentive to try to think about differentiation. Okay, maybe if I go a little bit further away, I can make some money, and not 0. And the other one's 2, right? But maybe not, because maybe the forces that bring it to the middle are too strong. So we need to figure out. So now we need to maximize profits, right? We need to choose P1 to maximize x hat times P1. Right? X hat is a function of P1. From 1. And from 2, let's do that side by side. So to maximize, choosing P2, 1 minus x hat times P2. Okay? So from 1, let's just take the derivative of this with respect to P1, right? First to the condition with respect to P1. And what do you get with this derivative? Well, let's just do it all over again. As if time were not an issue. So we have to take the derivative of this and do that at P1, right? It's going to be the derivative of x hat with respect to P1 times P1 plus P1 plus x hat, right? Plus x hat times the derivative of P1, which is equal to 0. And this is where the algebra started getting a little bit complicated. Okay, so the derivative of x hat with respect to P1 is minus 1 over 2 tau times L2 minus L1. And this times P1 is just P1 over this. And then plus that whole thing. P2 minus P1 over 2 tau L2 minus L1 plus L2 plus L1. Okay, now we can combine this minus P1 and minus P1 here. And so it's basically minus 2P1 here equals 0. Okay, and now we have to solve for P1. So basically, it's going to be P1 over tau and H2 minus 1 equal to H2 plus 1 over 2 plus P2 over 2 tau and H2 minus 1. And so now we multiply it times tau times H2 minus 1 and we're going to get P1 is equal to L2 minus L1 times L2 plus L1 is going to be L2 squared minus L1 squared again, and over 2 times tau, tau times L2 squared minus L1 squared over 2 plus P2 over 2. This is the best response function of from 1.
Jose, what are we here like maximizing the revenues?
Here the revenues or the profits, really, but we're assuming that the marginal cost is equal to 0. We don't have to, it's just to make the algebra a bit simpler. And that doesn't take away any insight. I mean, yes, it's like this minus the marginal cost. This the profits of from 1. And these are the profits of from 2. Now, another condition for from 2 is equal to P2. It's going to be similar. Right here it's going to be like the derivative of this. And this looks exactly the same as but let's just do it. Just flipping the ones and the twos, and then here we have to do 1 minus 1. So derivative of this is going to be minus P2 over 2 tau times L2 minus L1 plus P1 minus P2 over 2 tau times L2 minus L1 plus 1 minus L1 plus 1 minus L2 over 2 equal to 0. And then if we solve for P2 as a function of P1, we have to put like this P2 and P2 together. That's going to be like P2 over 2 tau times L2 minus L1 is equal to but just without the 2 because there's 2 of them, is equal to P1 over 2 tau times L2 minus L1 plus 1 minus L1 plus 1 minus L2 over 2. And now P2 is going to be equal to P1 over 2 plus a constant. So it's equal to 1 minus let's think about the constant first. Okay. So the constant before was here easy, which would be L1 minus L2 minus L1 times L2 plus L1. But now, if 1 minus L1 plus 1 minus L2, and here we have L2 minus L1. But as L2 minus L1, we can consider that the same as 1 minus L1 minus 1 minus L2, right? I'm going to use this. L2 minus L1 is equal to 1 minus L1 minus 1 minus L2. Okay, so with that, when we multiply times that, this is going to be 1 minus L1 squared minus 1 minus L2 squared. Is there a tau missing? No. So here, yeah, so that means times tau.
Tau multiplies.
Yeah, tau times 1 minus L1 squared minus 1 minus L2 squared. squared over 2 plus P1 over 2. So now we have the best responses from 1 and from 2. Now we can solve this 2 by 2 system for the equilibrium. So what does the system look like? Is there a shortcut here? Could we use like Kramer's rule maybe? Why don't we write the system in matrix form?
Okay.
Do we have to do this in the exam?
Yeah. You guys know Kramer's rule? Almost
Ah,
forgot it.
because we put it in the tool or in the.
No, I just think it's gonna look nicer with Kramer's rule. It's like we could solve here, we could substitute the P1 there and do it, like caveman style. But I wonder if we're gonna recognize algebra, we just go ahead and use Kramer's rule. Remember Kramer's rule? Kramer rule? The rule of Kramer?
Yeah.
Hammer? I don't know, it's French. And let's see if we can use that. So then we have to write in matrix form, right? So I'm just gonna have P1 minus 1/2 times P2, right? Is equal to L2 square minus L1 square times L2 times tau. Right? That's one, and then we have minus 1/2 times P1 plus P2 is equal to tau times 1 minus L1 squared minus 1 minus L2 squared. Okay, so now we have this system 2 by 2. We can rewrite it in matrix form as 1 minus 1/2 1 minus P equal to tau over 2 times H squared minus L squared and 1 minus L squared minus 1 minus I don't know. I just hope that the algebra is going to turn out nicer this way. I haven't tried it. Right? And so now we wrote it in this kind of nicer looking matrix form. Right? We have the vector obviously is B1 and B. It definitely looks like much more harmonic in matrix form. I don't know. Okay, so now Kramer's rule says what? Kramer's rule says that if we have a B, C, D times X equals E and F, then we have the determinant delta is the determinant of A, B, C, D, right? Which is equal to AB minus BC. And that's going to be the denominator, right? And then we're going to have delta 1 is going to equal to the determinant, substituting the first one for E and F, right? So the determinant of E, F, and D, which is E minus EF. Delta 2 is equal to A, C, and EF, right? That determinant is going to be AF minus BC. And then basically x1 and x2 is going to be equal to delta 1 over delta and delta 2 over delta. Is that correct? Or is there a minus and I'm correct? No.
I'm still copying.
Okay, so now we apply this to that system, right? So the determinant delta here, now delta in that case is going to be equal to 1 times 1 minus 1/2 times 1/2. So delta is going to be equal to 1 minus 1/2 times 1/2, which is equal to 1 minus 1/4. So it's 1 minus 1/2 times minus 1/2. So the minuses cancel out. That's 1 minus, which was 3/4. And then delta 1 is going to equal L2 square minus L1 square, right, from here, times 1. This times 1 minus minus 1/2 times this minus was in the plus 1/2 all of this and plus 1/2 times 1 minus over 2 times 1 minus L1 square minus 1 minus L2 square, right? Like this, and then all of this is going to be multiplied times the tau of 2, right? Because that's in both. It's both here and this one, and then delta 2 is going to be equal to, now this we substitute here, right? So it's going to be 1 times L1, and 1 minus L1 square minus 1 minus L2 square, and right, so we substitute here, and we have a minus L2 times minus 1/2, so it's going to be like plus L2 square minus L2 square over 2, and all these times over 2. But then of course this we have to divide it to obtain B1 and B2. B1 and B2 is going to be equal to delta 1 over delta, and so on. So it is going to be equal to this over 3 volts. So it's like tau divided by 3/2. It's like 2/3 times tau. Okay. So the 2/3 times tau we can put it outside, and then we have L2 square minus L1 square plus 1 minus L1 square minus 1 minus L2 square over 2, and then we're going to have 1 minus L1 square minus 1 minus L2 square plus L2 square minus L1 square over 2 times we said tau over 2 divided by 3/4. It's like 2/3 tau, right? Times 2 tau over 3. And now we can try to simplify this and this, right? So far so good? Maybe we have to like expand these things, right? And try to make this. Let's not simplify it out. Now we have to calculate the profit.
That's
This is crazy.
I don't think quite.
What's crazy is I'm doing this on the spot, like improvising this. But this is not crazy. Come on, guys. I mean, this isn't crazy at all. It's like we do a 2x2 system, right? 2x2 system. Remember, you can substitute the equation of the other one, right?
Yeah, by substitution.
By substitution. But we also have this thing called Kramer's rule. Remember Kramer's rule? Last time we did it by substitution. Last time we did it by substitution. But then the math got messy, you know, and then I just wanted to use this beautiful Kramer's rule. Explain the algebra will look at it nice. And yet it's the same math. You know, but I think that maybe you know it starts to be more symmetric. About, I don't know, I just feel like Kramer's rule, the algebra is going to be better because it's using the kind of like a slightly deeper math.
So we're doing Kramer's rule to solve our two linear systems of prices.
Yeah. We have a 2x2 system, two equations in triangles, P1 and P2. And we can solve it by substituting the best response to the other two responses, linear equations, or 2x2. There's two ways to solve it.
Which are those? These are the best responses.
Yeah, these are we have to solve the equation, this is not equation, so this is not, right? I come with the there, I just like we want them, it's by passing like all the prices to one side and the constants to the other side. Okay. This is not crazy. Maybe we did some algebraic mistake. But Kramer's rule is, I mean, did you see Kramer's rule, Raul?
Well, we kind of skipped that part.
we saw Kramer's.
I mean, the Kramer's of Kramer's rule. This is like Kramer's rule that we like calculus and algebra in college. And maybe we did
I saw it in calculus 1. But that's 10 years ago, I don't remember.
Yeah, now I remember. Kramer. I was an expert.
An expert seller of partisan battles.
Right. So now we have to calculate the profits, and the profits are the price times the quantity. Right? So now we have to do these times the x hat and 1 x hat. So the profits are for 1 as a function of L1 and L2 for the first stage. Well, 2. L2 squared minus A1 squared plus A1 squared minus 1 minus A2 squared over 2 times 2 over 2 times x hat. And x hat, what we have is here P2 minus P1, and now we have to replace
Joder, vaya función se nos queda.
P2 minus P1 there. We have already started. Now we have to P2 minus P1.
Tú si te quedas chorizo, morcilla, no se te queda todo. Pero vamos a un de lo que come en mi vida, no de lo que
Como entras a
Okay, so now P2 minus P1 we have to blend the equilibrium ones. So it's good. That's going to be 1 minus L1 squared. I'm just going to take it like in the side. Minus 2 squared plus L2 squared minus L2 squared over 2 minus L2 squared minus L1 squared minus 1 minus L1 squared minus 1 minus L2 squared.
P2 minus P1 shouldn't be 1 minus L2 squared minus L1 squared over 2.
P2 minus P1 is what? I'm trying to do it here.
Yeah,
L1
so
minus L1 squared minus 1
yeah, so
L2 squared plus L2
so it should be
minus this minus this.
so it should be the
This
first part
times this is-
exactly. The first part divided by 2 in positive,
Okay, yeah. Divided by 2.
and the second one in negative divided by 2.
Minus this. And all of this times
Tau
3 tau over 2. Right? Because also have the 2 tau. 2 tau over 3 or 3 tau over 2? 2 tau over 3.
Yeah.
2 tau over 3. But the 2 actually goes away. Because it's just tau over 3. Let's keep it as 2 tau over 3. Okay, so then this is 2 tau over 3 times that, right?
2 tau and 2 tau go out.
So this whole thing becomes
So it would be
1 minus L1 squared minus 1 minus 2 squared over 2 minus L2 squared minus L1 squared all over 2
exactly.
over 2 times 2, so it's really over 3.
No, but I said that I said
Now
that so
then the
that
tau's
we
going to
could,
cancel out.
exactly, so that we could cancel out the 2
That's
taus.
over 3, and it's really over 6, right? So it's also 2. So over 6 times L2
Exactly.
minus L1.
Exactly. Plus L2 plus L1 over 2.
L2 plus L1 over 2.
Yeah.
I mean, I'm a little crazy for doing this algebra here on the spot. I didn't have time to prepare this. I'm busy now. Yeah. But I think it's worthwhile doing this algebra. No, this algebra is not crazy. Think about it. It's just a little tedious. It just takes time.
It's
Okay.
adding and subtracting.
I'm worried because we're taking a lot of time off the class, but it's an instructive experience.
Do we have to do this kind of derivation?
No, not like the hot one. I think this is too long.
Not like the
Okay, yeah. I'm gonna try to not give you something with so much algebra in the exam. Okay. Don't think about this. Stop thinking about the exam, guys. Like, think about solving real world problems. Okay. Forget about the exam. Think about the real world. Okay. What happens in the real world? People do algebra like this in the real world. To do things. Why? Because people, economists in the real world, they look at the things that are going on, they get data, they look at empirical facts, they try to think about the world, and they try to theorize about the data. Theorizing means, okay, let's see if this data could be fit by a model of horizontal product differentiation, an endogenous location choice, or whatever model you may think of. Maybe you don't use this one, but you're gonna actually solve, like, if you're thinking of a real world problem, you're not gonna solve one problem. Like this. You maybe are going to try like 10 different models. You see what I mean? And it's not gonna take you like one day of algebra. It's gonna be like, okay, today we're gonna try this one. Okay? And I could tell you about like the kind of papers that I'm writing now and the type of model that I'm trying to solve. But it involves to algebra. Not always like as complicated as this. So this is something not like unreasonably complicated model to solve. It's just like it's not model that it's not like a totally toy. It's a toy model. It's not like a model that's so toy that it's like okay, I'm gonna solve for the equation in like 3 steps, and I'm gonna give you the answer, and it's beautiful, right? Like Coulomb, right? Or homogeneous groups per time. It requires a bit more work. Okay, I should probably not be doing it in class. I should be giving it to you as a homework, and you guys do it lab, and then I just say, okay, solutions to this, and that's it. Right? That's what I should do. I don't know why I do this now, because I think it's also instructive to do it and to see how sometimes things get not so easy and you get a little lost in the weeds, you know. But it's just like you have to do it step by step and keep it organized, and hopefully we'll get out of this. True. Make sense? Alright. Okay. So.
I have a question.
Yeah.
Where is the 2 coming from? The L2 square minus L1 square over 2.
Here?
Yes.
Where does it come from?
The 2 where is it coming from?
The 2 here?
Yeah.
These came from, remember, we actually wrote it down. We wrote like P2 minus P1 here, right? And then we have P2 is this, and P1 is that. So if you do this minus that, then you make like this one, right?
Minus.
Is 1/2 minus that one, that's like the whole. That's going to be like minus 1/2. So, and this one is like this minus 1/2 of that. So this one is 1/2.
That multiplied by this multiplied by that, right?
Yeah, so now I have to do this, times this, times
That.
this. Let's see if we can simplify this one by bringing
I'm saying
this.
the first equation is that multiplied by this multiplied by that, right?
And the profits, which is
Yeah.
what we want, are going to be this, times this, which is this.
Okay. So I just confused about these terms. One.
This is like,
I'm saying like the one L, 1 square.
this. Oh yeah, this is just like scratch. It's like scratch with P2 minus P1. So now we have that, we put it here, right? P2 minus P1. And let's do this. And now, now we have to put this up here. Right, L2 plus L1 over 2. That's going to be L2 plus L1 times L2 minus L1. Right? Because to bring it here, I'm going to have to multiply it as this. And it has a 2, so I have to make this a 6. So I have to multiply by 3. Right? So then this is going to be 1 minus L1 squared minus 1 minus L2 squared minus L2 squared minus L1 squared plus 3 times, this is going to be L2 squared minus L1 squared. All of this divided by 6 times first 6 minus 1. And now I can combine this one with this one, right?
Yeah.
So that's going to become this minus 2. Not minus 2, plus 2, right? Plus 2. Plus 2 is. Okay, this is starting to look nicer. Because now what happens if I take this 2 out? Now, that 2, if I take this 2, if I cancel this 2 with this 6, I can do that. And then I get 1/3, right?
I mean,
But let's not do that. We can take this 2 out and put it like a 1/2 here, and then we put the 2 outside. Right? So this is going to be this over 2, right? And now we put the 2 outside, it's 2 here, right? And now what is this? this over 1/2 plus this, right? So it's just like this squared. This whole thing and this whole thing are like one, actually, right? So it's going to be equal
Yeah.
to L2 minus L1, L2 squared minus L1 squared, plus 1 minus L1 squared plus 1 minus L2 squared over 2 squared. You see what I mean? Times, now I have a 2 and a 2 here, so it's going to be like 4, right? Over 3 times 6, 18, times tau and L2 minus L1. Over here. Right? So now we have a much shorter expression. So it's starting to look better. And let's see if we can do even better. I think we can.
I mean, we could first remove the 2, remove the 2 and substitute by 3 in the end. Or what? Huh?
I mean, we could leave it here, but it's not so bad.
Ah, yeah. 2, 9, yeah.
So it's right over 9.
12 over 9, yeah, that's the only thing.
This guy's like that.
That's the only thing I'm doing.
Okay. Well, let's see. We could take this 2 out of here and put like a 2 here. So 2 times this, take it 1/2 out, and then we cancel it out with the 4. And now let's get like this L2 minus L1 in here, squared. Okay, so now it's going to be equal, so L1, L1 and L2, it's going to be equal to 2 times L2 squared minus L1 squared plus 1 minus L1 squared plus 1 minus L2 squared over L2 minus L1 squared times all of the square times tau over 8. And now L2 minus L1 square is L2 minus L1 times L2 plus L1, right? L2 plus L1, and I'm going to cancel one of the squares. And then this is 1 minus 1 minus L1 minus 1 minus L2. Remember, here. L1 minus L1, L2 minus L1 is 1 minus L1 minus 1 minus L2. So this is 1 minus L1 minus 1 minus L2 times 1 minus L1 plus 1 minus L2. Right? So this is equal to L2 minus L1, which also cancels out. And then we're going to have 2 minus L1 minus L2. Okay, so things are simplified. So now we have 2L2 plus 2L1 plus 2 minus L1 minus L2.
Yes,
so
it's basically 2 plus L1 plus L2.
it's just 2 plus L1 plus L2. Okay. Alright. So now we have to take derivatives of these with respect to L1. Right? We should all should do the same for pi 2, but let's see, just to get a sense of like what the circumvention looks like. What happens if we take derivatives of this with respect to L1? Respect to L1 is equal to 2 times this without the derivative, right? And tau is tau over 18 times 2 times this, right? But this is like which is 2 times what's in the parentheses, right? Which is positive. Times the derivative of what's inside here with respect to L1, which is equal to L2 minus L1 times minus 1. Of course, times now times minus 1, right? Because there's a minus here. And then the square, and then times the derivative of this with respect to L1, which is 1 times this, which is L2 minus L1, minus 2 plus L1 plus L2 divided, times minus 1. So that's plus 2 plus L1 plus L2. And this derivative, right? This in parentheses, of course, is what's inside here, right? Just going to do it. This derivative, this is positive, greater than 0. This is greater than 0, and this, of course, is greater than 0. And then there's a minus 1, which is less than 0. Positive, 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 negative. This is always less than 0. Okay, so yes, this is another simplified expression for the profits of in the first stage of the game, right, as a function of locations. And then when we take derivative of the profits of first one with respect to location of first one, it's always negative. Okay, so there's no interior solution. Okay, there's no interior solution. It means I always want to drive my location to the left.
Do you remember what was like what were we doing? Like this is what we were doing.
The what?
Like when we say that that is lower than 0,
The
connecting
derivative,
to the
the derivative of the profits with respect to location from 1 is always negative. Transforms from 1 is always going to want the location
On the corner.
to go that way, right? L1. Until it gets to the boundary of 0. So from 1, it's going to locate at 0, and then from 2, if you do the algebra, which I invite you to, from 2, it's going to be positive. And it's always going to go towards 1. Okay? Basically, they're going to try to be separated from each other. Right? There's like a reduction of competition effect that's going to make them not go to the pure location equilibrium. Because now they realize that in the second stage, it reduces their profits too much if they're next to each other. So they actually try to separate as much as possible. You can, in some other versions of this game, you can have that we kind of stabilize. If this game were played like an infinite line instead of 0, 1, then they stabilize maybe like, I think it's like a minus 1 point. To use an example, at some point, the market location effect start to put them back together. So in this case, they go as far as away as possible. There's some versions of this game in which there is a material solution. And in the line where if you expand the line, they will actually locate in some intermediate point, not at the center, but also not like going to minus infinity and infinity. Okay? This version of the game is 0, 1. Basically, it pulls them here. The competition effect, the reduction of competition effect, fully dominates the location effect. Okay? The market size effect. And so they get pulled all the way to the limits. Alright? It wasn't that bad, guys. It's just it took me an hour and a half, and I should have been giving you more models. So I look stressed out because I'm like, you're supposed to go like 5 more location models or something like that. And we spent like hours doing this one. And then it wasn't that bad. Look, Ferrari column. We found, let me recap for you. Okay? Let's recap. That's nice, right? Quadratic coupling, utility function, right? Depends on the reservation value and minus the price, minus the transportation cost, which is now quadratic in terms of the distance of the person and the firm. Okay? The transportation cost now increases quadratically with the distance to the firm. We want to locate, to calculate the demands, we want to locate the indifferent consumer. Right? Everyone who's to the left of the indifferent consumer is going to iPhone from 1, the one to the right is going to iPhone from 2. We solve the little equation here, nothing fancy. Different consumer, x hat is given by this linear function of the prices. Okay? When the constant is L2 plus L1 over 2. Beautiful. And then we have the same equation for the second, right? Then, now we solve the price competition game. So we maximize the profits of from 1 with respect to P1, and we maximize the profits of from 2 with respect to P2. And what do we find? The best response functions, which are linear. Easy. These are the same as the differentiated goods per tram. Okay? The locations are different, but the differentiation now is micro-founded with this location. Now, we calculate using this fancy piece of mathematics from high school called Kramer's rule. Okay, we can also have done the substitution, right? And then that gives us this beautiful equation for the prices in the second stage. Okay, but then we want to solve the super game, right? So now we have to plug in this and say, okay, if this is what's going to be played in the second stage, now where would they choose to locate in the first stage? So we have to say, okay, now we're plugging these equilibrium prices, the equilibrium on the second stage, in the profit functions, and calculate the profit functions, but think of them as purely a function now of the locations, because the prices are a function of the locations in the second stage of the equilibrium. Okay? Depending on where we locate, we can expect some prices to be there in the second stage. Okay? This is where the algebra got a little bit more difficult, but in the end it was beautiful because this part can simplify into the same as this term, and then we get like this square term, and we have tau over 18 here, which is kind of like a good number, 18. But you know, it's not that bad. It's not that mysterious. We have two terms, it's not like suddenly pi appeared here or something. Okay, or the Fibonacci sequence or something. It's not. Okay, so now we got our equation, and now that it's simpler, we can take derivatives and we get like so confused like before. Now we can easily see when the derivative has a negative sign, and therefore it's not going to have the solution, to equate it to 0. And that means that because it's negative, that's like the force that's pulling the firm towards 0. And the other firm is going to pull towards 1. And so we get a Nash equilibrium of the super game with maximal product differentiation. What? This is the super game. The super game is the super game equilibrium is super game perfect Nash equilibrium, remember this, is what? It's a Nash equilibrium in each of the subgames, and including the super game, which is considering both the first stage and the second stage. Right? Here we have like subgames, right? Depending on what you do in the first stage, depending on the locations that they choose, they're gonna play a different subgame in the second stage, right? For every continuously infinite number of possible locations of from 1 and from 2, there's a different game to be played in the second stage, right? Each of those is called a subgame of this model. You see what I mean? Each of those has to have like a Nash equilibrium, which is like the idea of Kramership, right? So we have to calculate the equilibrium for every possible thing that could happen, right? Any possible pair of locations, right? If they're the same, it's going to be homogeneous to the parameters and 1 to 0. But then, for any different pair of locations, such as any, we have to solve the Bertrand equilibrium for any possible thing that could happen. Each subgame, each possible subgame. So the super game, subgame perfect Nash equilibrium of the super game has to be a Nash equilibrium in each of the subgames, right? So we're using those values and substituting them into appropriate functions, right? And that implicitly what it's doing is it's imposing the subgame equilibrium in each of the possible subgames that we play. You see what I mean? They're like, they know exactly what's going to be played no matter in each of the possible branches of the 1 and 2 decision, right? And now we go back to the 1 and 2, and it's like, okay, given that they're going to play the Nash in the second stage, in the subgame, now we solve for the Nash of the super game, right? The subgame perfect Nash equilibrium. And for that we have to take the first definition of this. But then when we do that, we realize actually the solution is the best thing that we can do is this one goes east over what? This one goes this way as far as possible no matter what. They do maximum cross differentiation. Maximum product if okay? We've been running for like an hour and a half. Let's just do a little break. 15 minutes and let's keep back here at 1:15. Okay.
对，一般他就是第一节课提前下课，后来这个到点下课。有的时候还做堂。
接夫人约好了。
接夫人？他不是走了吗？
明天后天才走。
还没。
没事，说你走了。
那他来找你吃饭了？
对啊，去食堂。没告诉别呗。但是我们说2点半，我跟他说我们可能会提前下课，但是
没事，让他等着，让等着吧。
我也是想让他等着。
对。然后明天交作业，不是后天交作业，明天还有1天，没事。
他那个答案好像很省略。
他好像说他答案好像是 AI 生成的。
啊，这样子难怪呢，很省略的。我觉得那个超过2个数字啊。
对啊。
What is this? Okay. Okay. So